A transistor-based feedback amplifier circuit is analyzed in this example with 3 stages designed using one N-channel JFET as its first stage, and then we can see we have a P-type BJT or bipolar junction transistor as the second stage, and then an N-type BJT as the third stage. The combination of P-type and N-type formed a semi-Sziklai Darlington pair in this circuit to boost the current. We want to analyze how the feedback in this circuit is working, like this feedback that we have, and we want to find the open loop and closed loop voltage gain from Vin to Vout in this circuit. Vin is a small signal 10 millivolt sinusoid with plus minus 10 millivolt peaks, and we want to find out what Vout we have. Take a note that we are not doing the DC bias analysis because we make the assumption VDD and the supply and of course the other side ground properly used and applied in this circuit, so that the BJTs and JFET transistors are all in proper DC bias for proper small signal operation. For just to understand what is going on, so we have Vin applied at input, and then a portion of this Vin appears between the gate and source, so gate, source, drain of the JFET transistor, as we are, let's say, adjusting or changing a small variation in between the gate and source voltage of the JFET transistor that result in change or variation of the current of the drain of JFET, which then result in correspondingly a proportional change in the current of the base of the P-type. Let's say if this is T2 and this is T3, the second and third transistors, then IB2 is changing. IB2 changes, as a result the current of collector 2 is changing, and then when that is changed, there is a current division between these 5K and the base of transistor T3, and therefore I base 3 is changing, which result in finally an adjustment. So let me just make sure that I'm showing the direction of current correctly, avoiding any future confusion. So IC2 is changing, and then IB3 is changing, and as a result I-emitter 3 is changing, which result in output voltage variation. So that's the big picture of what we are playing here. For the N-channel or N-type JFET, as I said, we are not doing the DC bias analysis, but because I have to make a couple of assumptions, then it's important to notice what we have. So here is the IV curve, IV plot for the current of drain and the current of and the voltage of between the drain and source for the JFET transistor. When I say it's properly biased, just a reminder that I mean that, let's say we set the VGS at, as an example, for DC bias, you can see that as DC bias, because of this sort of decoupling, this coupling cap that we have here, then DC bias wise, this node is grounded. So the gate of the N-channel JFET is grounded, and there is a DC voltage at source. Therefore, there is a negative voltage between gate source. Let's say that negative voltage is -2, for example, VGS of -2. Let's say for a VDS of flat, just 7 volt as an example, or 6 volt or 7 volt, we are here. So I can make the assumption that this is the bias point for DC bias, with 7 volt between the drain source of the JFET transistor, and then we have about 5 milliamp between for the drain current. Now we can see that if VGS, because of the AC variation, for example, change, just as a benchmark, if for instance there is a 1 volt change in gate source voltage from -2 to -1, then we can see that assuming VDS is kept at fixed 7 volt, then there is an increase in current of drain of the JFET by about 3 milliamp. So these are amp, and therefore this is 5 milliamp roughly, this is 8 milliamp. So you're seeing about 3 milliamp increase in current for increase of VGS from -2 to -1. Basically what we refer to as transconductance, or GM of JFET, which is the change in the current of drain as a function over change in the voltage of the gate source. So 1 unit change in voltage of gate source, how much change in current of the drain we get? Let's make the assumption it is 3 milli Siemens or 3 milli mu inverse ohm or ohm inverse. So let's make the assumption that is about 3 as shown here as well. So I just wanted to highlight that when I say GM or transconductance is 3 milli, let's say Siemens, then what it means? It means 3 milliamp increase in ID when for a fixed VDS when VGS is increased by 1 unit. Okay, so with this clarification in place, I can now proceed with the analysis of the gain of the circuit. So let's make the assumption that in this given circuit, therefore, based on this prelude, we have this information. So we have for JFET or junction field effect transistor, we have R of the gate or resistor seen when we look at the gate of transistor is practically infinite, so we are not worried about that. Let's make the assumption that the transconductance, as we just talked about it, is 3 milli Siemens or milli-mu. So all of them is the same thing. Ohm inverse, and then what else I need to make the assumption? I think that's good enough. Let's make it proper. Let's also assume that it's properly DC biased, as we talked about. For the bipolar transistor or BJTs, let's make the assumption that the beta or the current gain of transistor IC over IB, I collector over I base for both P-type and N-type is 100. It's a practical assumption because these transistors are low current transistors. And let's make the assumption that the resistor seen from the base relative to emitter is equal to just 2 kilo. This is sometimes referred to as HIE in the equivalent model for transistor. And let's also make the assumption that again, BJTs are properly biased, and also I'm looking at R collector. So R collector of the BJT transistor practically is very large. So I'm talking about, say, on the order of 200 kilo ohm. So we can basically neglect that in this circuit, you can see. So very large. Okay, so what are we then looking at? First thing to do is notice the operation of the feedback. The Vout at the output of the circuit is going to have feedback loop back into the gate source via a division of 25K and 0.5K. So it's as if when you think about Vout, there is Vout and then there is 25 kilo ohm and 25 kilo ohm, and then there is this 0.5 kilo ohm. So it's as if whatever voltage appearing right at the source of the field effect transistor is going to be 0.5K divided by series of 0.5 and 25K. So it's like a voltage division between these guys. So what we have is 25.5. It's as if 1 over 51, the feedback, let's say, gain or beta of this circuit. Reason for that, the reason I mentioned about it is because let's say if you apply voltage here at gate and you increase the voltage, you are increasing VGS and therefore you are trying to increase the current of drain. At the same time, when that happens, the increasing VGS increases IB2, increases IC2, and then increases as a result IB3, increases the IE3, and then increases the Vout. So naturally, when you increase the VGS, you are increasing the Vout, but then Vout increasing will result in correspondingly proportionally via this resistor division an increase in Vs, and therefore it's counteracting the increasing gate because source is now catching up. So it's clearly a negative feedback. The reason I mention about this is double checking that we have a negative feedback, not a positive feedback, and it's a voltage feedback, because we can clearly see that the output voltage is divided between these two resistors, to sample it, basically to sample output voltage a 50, so with a factor of 1/50 roughly, to get to a source and then counteract what was happening at the gate. So it's a negative feedback, and the type of it is a voltage feedback. Alright, with that in mind about what's happening in terms of the feedback in this circuit, let's just remove, to do the analysis, I need to do the open loop circuit analysis and find the open loop gain. So let me just remove the feedback resistor in this circuit, which is this one, for now. So I'm going to put it aside, and my circuit is open loop now, and I just need to find the gain here. Okay, let's do it quickly. It's not difficult. So what I'm going to do is this. From Vin, I have a voltage division between RS 1 kilo ohm. That's the source resistor, and I have effectively the circuit is starting from this point. So this is my Rin or Zin, the input impedance, which is effectively just, given that we are making the assumption that the input impedance of the gate of the N-type JFET is infinite, Rin is effectively 0.5 mega ohm in this circuit. So with that in mind, I can just move on and say that this Vin is doing a voltage division between 1K and 0.5 mega ohm to get to the V gate. So this point is V gate, VG. And we are doing a small signal AC analysis. Assume that the DC bias is properly set. So I can say V gate is equal to 500 kilo ohm, which is this 0.5 meg resistor, divided by 1 kilo ohm, which is RS, and then plus 500k times Vn, which is practically just Vn. So I get this. I'm going to write it here. V gate is equal to approximately Vn, practically speaking. Okay, so this is our equation number 1. Let's keep it. Now, from V gate, we need to get to VGS. And there are two voltage components. There is plus minus VGS, of course, and there is also the voltage drop across this 0.5K resistor. So I'm going to write it this way. V gate is, I can write it here actually. So I'm going to write it V gate, VG, so let's put it this way. V gate is equal to VGS plus this voltage drop across 0.5K, which is 0.5K times AC current that is coming from drain, this current. So this current that is coming from drain of the JFET. So I can write 0.5K times ID. But then ID, we know that ID is just GM, the transconductance, times VGS. That's the definition of GM. So I'm going to write it here. So it is basically just the change in current of the drain divided by the change in voltage of gate source here, which is exactly what I did. So I'm going to substitute then. V gate is equal to VGS plus 0.5 kilo ohm times ID is GM VGS. Great. I can factor out the VGS here. So VGS times 1 plus 0.5K times GM is 3 milli, so kilo ohm, and then milli ohm inverse Siemens. So as a result, I get VG is equal to 2.5 times VGS, or alternatively I can say VGS is equal to 0.4 times V gate. That is what I needed. So I found VGS is 0.4 V gate. So whatever V gate appear at the gate of the JFET contribution of Vn is basically 0.4 Vin will get to 40% of Vin will get to VGS. So all Vin will get to Vgate, but then from Vgate to VGS, only 40% of Vgate gets to VGS. That's the meaning of this. Okay, so let's name this equation number 2. So equation number 2. Now, what else do I need? I need to then, now that I have VGS, I need to get to I base of transistor 2. So let's do that. Let's do, so this is ID1, which means the current of drain of the transistor 1. Now let's do IB2. So IB2, here we have ID1, and you can see that there is basically a current division between 10 kilo ohm resistor and whatever resistor observed here, which is basically just RB of BJT, because emitter is effectively AC grounded. So whatever DC voltage here is not changing AC wise. Therefore, from perspective of AC analysis, it's as if we have AC virtual ground here. So therefore, the resistor observed from this node, AC equivalent impedance, is just the RB that is given to us, this one, 2 kilo ohm. So I'm going to use that. So to get to IB2 from ID1, I need to just do, so I'm going to write it here. So the best way to show it is this way. I have ID1 and I have a 10K, which is AC grounded, virtual ground, and then I have an RB for transistor number 2 for P-type BJT, and then I have virtual ground. So I need to find this IB2. So I need to find this IB2, which I can do a voltage division between, current division between 2K and 10K. So to find that, I can say IB2 simply is a current division, and that is 10 divided by 10 plus 2K times I drain of 1, which means 10 over 12, which is 5 over 6, ID1. Okay, great. Now, I need to get to IC2, of course. That's my target. So I can say IC2 naturally is beta, or HFE, times IB2, the current gain of the P-type BJT. And then substituting from here, I can say is beta 5 over 6 times ID1. And ID1 is GM-VGS, so I can just do one shot. So ID1, let's put it this way. So I'm going to use it here. I'm going to say is equal to, knowing that ID1 is GM-VGS, therefore is going to be beta, and then IB2 is this, so 5 over 6, and then GM VGS. GM is 3 millisiemens and beta is 100, so it will become 100 5 over 6 times 3 millisiemens, or mu, and then VGS. In summary, what I got is IC2, this current coming out of the collector of transistor, P-type bipolar transistor, is equal to, I get from this writing, is equal to, I have, let's just make sure I'm not making a mistake here. So what I get is 5 over 2 and then times 100. So I have 5, so it's 250, of course, milli, and then we have VGS. So let's keep this as our equation number 3. Okay, now that we get to IC2, it's not difficult to get to IB3 with the same idea as we did as in the sense of a current division between ID1 to get from ID1 to IB2. Same idea. I want to get to from IC2 to IB3, so I need to find equivalent impedance observed from the base of transistor T3. So from that perspective, it looks like something like this. So I have IC2 coming, and then I have a 5K grounded, this 5K, and then I have the RB3 for the transistor T3, the N-type BJT, and then I have the 300 ohm that is transferred to base by multiplying it, because I'm moving it from emitter of the transistor T3 to base of transistor T3. I need to adjust for the current reduction by beta plus 1. So I get plus HFE, or beta plus 1, the current gain plus 1. Plus 1 is because it's emitter to base, not collector to base, times 0.3 kilo ohm. 300 ohm is 0.3 kilo ohm. So that is what I see, and that's AC grounded, virtual ground. Then this is the breakdown. So the RB3 is again 2 kilo ohm, and then we have beta plus 1 is 101, and times 0.3 kilo ohm. So this becomes obviously 2 plus 30.3. So we get out of this one 32.3 kilo ohm. So basically from IC2, I need to do a current division between 5K and 32.3 kilo ohm to get to this current, IB3. This is my target. So IB3 is equal to 5K, so 5 kilo ohm, divide by 5 kilo ohm plus 32.3, which is times IC2, which is going to be, just before the last step, 5 over 37.3 times IC2. Okay, so the last stage is so I got IB3, but then from IB3 I need to get to IE3, which is not difficult. I just need to multiply by beta plus 1. So what I'm going to say is this: V out is 0.3 kilo ohm, so 0.3 kilo ohm, this resistor, times IE3, but then IE3 is beta plus 1, or HFE plus 1, times IB3, and then IB3 is this one. So I'm going to use it and write V out is, and this one is obviously 101 because beta is 100. So I'm going to get 30.3. That's this multiplication, and then IB3 is, and this is K, of course. So just to make sure we are not missing something, this is stealing K, and then we have 5 over 37.3, and then we have IC2, in which I use this outcome. Alright, so this is equation number 4, and we are done. Reason for that is I can now trace everything back to the origin. V out is related to IC2. IC2 is related to VGS. VGS is related to VG, and VG is related to VN. So this means I can use combination of equations. I'm going to write it here. Combination of equation 1, 2, 3, and 4. All of these guys will give me this outcome. V out is equal to 30.3K times K, meaning there is a factor of 1000 here, times 5 over 37.3. So this equation. Now I'm going to substitute IC2 using equation 3. So using equation 3. So that means I'm going to write 250 milli Siemens. So millimole, or ohm inverse, Okay, so let's just write Siemens. And you can see milli now cancel out the K. So these two cancel out each other. Effectively, that's good. And then now VGS is substituted from using equation 2. So it's going to be 0.4. And then VG finally is going to be in the equation 2 is going to be substituted using equation 1, which means Vn. So if we compute the whole thing, then we get to this nice outcome. V out is roughly 406 roughly in this circuit times Vn, which means open loop gain, so AV open, gain of voltage gain open loop is roughly, which is V out over Vn, which is V out over Vn is roughly 406 volt in this circuit. So I'm going to just highlight this. We found the open loop gain. We are almost done. So this circuit has a considerable open loop gain. That's interesting. Now, the only thing I need to do is understanding the feedback, as I mentioned. So feedback is, of course, a voltage feedback, negative, as we discussed at the beginning of the circuit. So how does it look like? It looks like exactly like this. So it looks like we have Vn coming in, and we have Vn applied at the gate, so it becomes Vg. So it contributes to gate, and then we have let's say Vin contributes to VGS, and then at the same time we have the contribution of the output, as we talked about, as a negative contribution to VGS. And the way it's done is using a feedback gain beta. So I'm going to write it here, which we found it to be 1/51, which is in the circuit, as you remember. Now if I return, so I'm going to, just for the sake of illustration, I am going to return this feedback resistor here. So put it back. There you go. Okay, so circuit looks like this, and you can see we are now dealing with V out contributing this way to VGS. And as we talked about it, there is a voltage division between 0.5 kilo ohm and 25 kilo ohm. And the good news is this 25 kilo ohm is not affecting the input impedance in terms of the 0.5 kilo ohm contribution or the output impedance scenario. So because 300 ohm is much smaller than 25k in series with 0.5, so we can neglect the impact of 0.5 at the output. At the same time, 500 ohm is considerably smaller than 25k series with 300. So again, contribution of 25k feedback resistor to existence of 0.5k at the input is minimal, negligible. So we can say whatever we did for the open loop voltage analysis and finding this AV open loop using the circuit that we analyze is still valid. That's something we always need to be careful about. So now I can say what I found for the open loop, AV open loop, is still valid. It will give me V out, but then V out is fed back. So let me put it this way. But V out is fed back via the negative feedback route, which, as we talked about, it is 0.5k divided by 0.5k plus 25k, which, as we saw, is 1/51. So that is the beta, the voltage gain of the feedback resistor setup. And then from output V out, we are just grabbing and applying to, from output V out, we are just getting a sample and apply it to that feedback route. So in this setup, just not memorizing anything, but just quickly show, we have Vin minus beta times Vout. So that that is the voltage here. So what I showed you is now here, and then multiplied by AV open. So multiplied by AV open loop, going to give me Vout. So as a result, when we reshuffle things, moving this portion here, what I get is Vout over Vin in this feedback loop is equal to AV open divided by 1 plus beta AV open, the famous feedback gain equation. So if I substitute, then I'm going to substitute 406 for AV open, and I'm going to substitute 1 plus as we computed for beta 1 over 51, and again 406. So that gives me the feedback gain, voltage gain, so closed loop basically voltage gain in this circuit, which if I do compute quickly, it's going to be roughly on the order of 45 if I remember correctly. So 406 divided by 51 is roughly 8. It's effectively 406 divided by 9. So 45.3 roughly. So therefore this is, I'm going to write it here. So AV feedback or closed loop, AV effectively, is equal to approximately 45.3. That's it. That's the voltage gain for the closed loop circuit. Alright, so I hope that this example, extensive example involving JFET and BJT P-type, N-type transistors in a 3-stage feedback amplifier is helpful in terms of highlighting and showing how we can deal with a voltage feedback in a circuit that is shown here. We analyzed how the JFET is working, and then we went stage by stage by seeing how input voltage is traversing, and by chasing the current. Vin results in small signal variation in Vin, results in a small signal variation in VG, results in a small signal variation in VGS. That translates to a small signal variation in ID1, that result in change in IB2, that result in change in IC2. As a result, IB3 changes, and then that will make change in IE3, and therefore via 300 ohm it will adjust the Vout with the open loop voltage gain of 406 and with a closed loop voltage gain of about 45.3. I hope that this example is helpful. Thanks for watching.